I'm going to make a start. So thanks everyone for coming for this session. We're going to be looking at this thing called mypy and looking at how we add typing into Python. So there is some materials for this, but you don't really necessarily need it. It's perhaps more useful for kind of later. Just going to turn this microphone down a little bit. Okay. I just felt like it was kind of at the edge of feeding back. Can you still hear me okay? Great. So yeah, the material, you don't need to do a notebook or anything. I'm going to be writing code. You can sort of do it with me, but you don't need to really have anything particularly to start with other than mypy installed, but it might be useful to look at later. So I'm going to start with a little bit of a warm-up. So I'd like you to tell me the answer to this question, or what does this expression evaluate to? We're going to start really easy. 2. Great. Thank you. OK, how about this one? What? Going to be an error? Depends what language. Yeah, right answer down there. Yeah, very good. So does someone want to give me some possible answer? Hello 1? OK, yeah, hello 1. In JavaScript, that's true. So JavaScript will do something here. It'll take this 1, and it will look at the type of this thing and say, oh, that's a string, so I'm going to turn this into a string and concatenate it. Maybe you could kind of imagine in like an assembly language, something like this kind of code. OK, it won't look exactly like this, but it could give you something like yellow, because you take the ASCII character, the ASCII code for H in the memory, and you add 1 to it, and it becomes for I. Or depending on the memory layout, maybe you could imagine something like that might happen. But yeah, it depends on the language, right? There could be some meaning for this. Or someone said over here, oh, it could be an error. I think in many languages, this would be an error. How about this one? Hello times 2. Hello, hello. Yeah, and that's what happens in Python. So Python, that's how it implements this, this particular expression. How about this one then? So a little bit tricky. I don't know of any programming languages that have a meaning for this. So this is something a little bit harder to work out perhaps what you would want to do. So the point of this slightly silly exercise is to think about the fact that when we have a language, the types, part of what the types do is that they communicate to us, the programmer, what the computer can actually do. So the typing can tell us when an operation is defined, what it's going to do with it. If we don't know, hello divided by 2, then the types are telling us, I don't know how to deal with something that takes a string and an integer and gives something back. So types are partly about communicating to us what the language will do. So what we're going to do today is we're going to understand some of the key ideas that are behind concepts like specifications and verifications. So I'm going to start like a little bit high level with this session. It's going to be a little bit more like on the lecture end at the beginning, just thinking about some high level concepts in software verification. We're going to look at some of the concepts and terminology that goes behind types and type systems. That's going to be a little bit more general, not completely specific to, say, Python mypy. Then we'll get into using mypy, become more practical. We're going to write some code. I'm going to be doing a bunch of live coding. And generally, we're going to be thinking about, well, hopefully by the end, you'll have developed some ability to avoid bugs in your code using mypy, and that this will help you write code more effectively. So do stop me at any point. Do ask me questions. I'm not going to be talking for an hour and a half. There will be a bit of time for you to do some exercises as well, but do interrupt me. So thinking, kind of going up to 10,000 meters high and thinking more generally, the way I think about software and scientific software is to think about what does correctness mean in this context. So in a scientific context, there are kind of two kinds of correctness we think about: validation and verification. Validation is, did I implement the right equations? And verification is, did I implement the equations right? Validation is the sort of science part, right? Am I doing the right science? Is this really a model of moist convection. And verification is, well, did I implement the code in the way that I intended? Does it do the thing that I wanted it to do? Now, it can be, depending on what you're doing, there can be a bit of a challenge. If your code does something that you didn't expect, it might be a validation issue, it might be a verification issue, and kind of telling these two apart can be quite difficult. And that is one of the challenges in computational modeling, in climate modeling, in Earth systems modeling, in any kind of this scientific domain, because you're kind of grappling with these two things, the science being right and the code being right, and they get kind of mixed together. Today we're going to be focusing on this verification part and trying to make sure that our code does what it's supposed to do and that we've implemented what we've intended. So we're going to be on this kind of verification side. So what do I mean, though, by verification? What does it mean to verify a piece of software? Well, you have to think about verified with respect to some specification. It's not enough to just say, oh yeah, I verified this code. Well, you know, verified it against what? You have to have some specification with which you're saying it conforms to that specification. So usually in any kind of sort of verification activity, what you're doing is checking that the implementation via some procedure conforms to some specification. So in a sense, you could think that you could see that validation is a kind of verification, but where the specification is some observational data, or sort of roughly you're kind of checking up to some kind of approximation with respect to the observation. The key thing, though, is that the value of a specification is what we make of it. It depends on our goals and our values. And having a specification and verifying code against it is great, but specifications can also be wrong, specifications can be incomplete, so it's sort of not the whole story. We have to think about how much specification do we want to put into our code, and what can we do to kind of check that our code conforms to it. So there are lots of verification techniques. Hopefully you're familiar with this very classic and very usually relatively easy to deploy one, which is testing. That's a great verification technique because it uses the syntax of our language as we already have it, and it's a way of us providing specifications, these tests, and the test framework where we run these tests is doing that checking. It's checking, does the code satisfy these tests? So the tests are our specification. Type systems are another kind of verification. So Fortran is a programming language where you have to declare the types of your variables, and when you run the compiler, it applies the type checking algorithm that checks, does your code conform to these type specifications? So that's a verification procedure, and it's cutting out various bugs. There are lots and lots of other kinds of verification approach that exist out there. Almost none of them are applied in climate sciences, earth sciences more broadly. I think that's a shame, but most of these tools are not developed to. Unfortunately, people don't put enough time into making them deployable by scientists, which is a shame. I have done some work in that area, but that's not the topic of today. We're going to be focusing on types. Yeah. Oh, it's not that they're not applicable necessarily, it's just that they're not necessarily very usable by people outside of the circle of kind of computer science where these are developed. So it's not that they're not necessarily applicable, it's just the accessibility of them. So I think that it's absolutely the case that we could be using static analysis tools in Earth systems. It's just the people who develop those don't necessarily spend much time looking at computational science code. Oh, it's just the sociological aspects of the training materials and the accessibility and how do they work with other processes and tools that are used in that area. So it's more like the human aspects, I'd say. Yes? Yeah, okay, so the question is, what are these things? So that's not the topic of this talk, but I'll do it very quickly. So deductive verification, these are systems of being able to insert pre- and post-condition specifications within your code and then having a tool that checks them. So for example, if the input to this function is greater than 0, then the output should be less than 360 or something like that. And then there are tools that check, will the code actually meet those specifications? That's known as deductive verification. Static analysis is when you have some sort of agreed specifications up front, like dividing by 0 is bad, and a tool will analyze your code and work out, does it contain any divide by 0 errors, or does it contain any memory bugs? There might be other specifications you can write along that. It's a technique where your code is automatically analyzed with respect to specifications. Interactive theorem provers is basically a sort of a maths language where you can describe proofs. You have a program that checks the correctness of those proofs, and they're used a lot to prove properties about programs mathematically. You have to have a good semantics for your language to do that. Modeling and model checking is when you have a procedure that takes code, generates a model of that code, and then you ask questions about that model, usually using logic, and then there's a logic engine that checks, does that model satisfy that logical specification. Used a lot in processor manufacturers use this a lot to get rid of bugs in CPUs, which cost them billions of dollars when it happens. So yeah, happy to talk more about those offline. Okay, so I'm going to chuck this quote up here, which comes from a really lovely thought piece about verification and formal methods. There can be no point embarking on the construction of a specification until it is known exactly what the specification is for, which risks it is intended to mitigate, and in which respects it will inevitably prove inadequate. So this is really getting back to this, like the value of the specifications. We have to sort of understand what those specifications are for, what they're going to guard against, what problems they're going to mitigate against, and which things they don't. So for us, we're going to be looking at types. They mitigate against data errors. They give us a framework in which we can check that a program doesn't have certain kinds of error relating to the form of the data that we expect. It checks for those and makes sure that we kind of get rid of those ahead of time, rather than running our program and eventually getting to a point where some data gets corrupted or some memory gets corrupted or something really bad happens to the data. Now, Python does already have a dynamic type system. So Python, if there is a kind of data error, won't just sort of do something weird and trash the data. It will give you a runtime type error. And I'm assuming here that everyone has written Python and will have come across these runtime type errors before, but they happen sort of later on once you're running the program. So it could be 2 hours into a run on your cluster that this type error happens, and then you've done 2 hours of work for nothing because you eventually hit that type error in your code. With mypy, we're going to be checking for those errors ahead of time before we even run the code. So this is known as static typing. So this helps us eliminate bugs. There's this kind of well-known phrase in computer science by a person called Robin Milner. He won the Turing Award in the 90s for the work that he did in the 60s, 70s, and 80s on programming. He said, well-typed programs cannot go wrong. Okay, this is like a bit of an aphorism, bit of a kind of, doesn't tell you the full story, because we have to say, like, for some definition of wrong, right? Just because you have types doesn't mean that your program won't do something that you didn't expect. It's just that it won't have one of these data errors. So those are the kind of things we're guarding against. So we're going to think a little bit about what types are, and we're going to learn a tiny little bit of notation and syntax from mathematics, which we'll then kind of use later on in this course. So a helpful model for types in mypy and Python is to think of types as sets. They're describing a set of values that can be produced by an expression. So if you've done any kind of discrete maths at any point in your life, you've perhaps done a little bit without realizing it. We often think of sets like the set of natural numbers, which maybe starts with 1 or starts with 0, depending on which department you've come from. Or like this thing Z, the set of integers, which has the negative part as well, or R, the real numbers. So these are sets of values, and they could be infinite. If we have two sets, A and B, we can make the set of pairs by doing the Cartesian product on those sets. So that, if, for example, if we take the set of natural numbers and take its product with the set of natural numbers again, then what you're doing is describing a set of pairs of natural numbers. So 1 and 1, 2 and 1, 2 and 2, and so on. So these are like tuples that we have in Python. Now, functions are something that we often want to describe in mathematics, and this notation of the arrow is used. So if we want to describe a function that maps from elements of the set A to elements of the set B, then we write this down as A arrow B. And this thing is itself a set. You can think of it as like a set of pairs where everything in A has at least has something in B associated with it. So, for example, we could have the abs function, which maps from integers into the natural numbers. I've put 0 here. This is a notation for the natural numbers that does include the 0. So here I've used a little bit of notation already, which is this colon here. It's a way of associating to a mathematical expression a type, a specification of that expression. So the kind of syntax is expression, colon type. That's our specification. We sometimes call that a type signature. And we're going to, that's the notation that comes from mathematics, and we're going to use that today as well. Okay, some other examples. We might have the square root function takes a positive real number and gives us a pair of real numbers back because the square root of 16 is -4 paired with 4. Or we could think of plus as it's a function that takes 2 inputs. We say its arity is 2. Arity is a way of describing how many arguments, how many parameters, how many inputs a function has. So it takes, we can describe that as a pair like this. Takes a pair of natural numbers and gives us a natural number back. Okay? So, okay with everything I've said so far? Just a little bit of background theory? Great. So, I've already mentioned this kind of static typing versus dynamic typing dichotomy. So, okay, you might be familiar with Fortran. It's one of these statically typed languages. The compiler does the type checking for us ahead of time. If a program, if the type checker says, no, you've done something wrong, this is ill-typed, we say, and the compiler rejects it. And in a sense, if the Fortran compiler says this is ill-typed, we think of this as basically not being a Fortran program. It has no meaning apart from its types. If it's not well typed, it's not valid, we can't run it. So this is a concept called intrinsic typing. And if the type checker says, no, this is fine, we call it well typed, and then the compiler goes on and compiles it. And in the case of Fortran, the types are used very, very heavily then to optimize the code. In Python, it's dynamically typed, so there are no checks ahead of time. We just start executing the code. Data is always stored with its type information, so inside the running code, Python can inspect a piece of data and say, what is its type? And then the operations use this to then work out what to actually do with the bits of data that you're around. They will check the type information. That then tells the system the structure of that information and tells the operations what to do. Now, as I said, the errors occur sort of as they happen. It's not that Python doesn't have any typing. It does have typing. It's just dynamic. It won't just sort of do something badly with the memory. It will say, no, these things don't have the right type. So hello divided by 2, Python will give us a runtime typing error saying, no, I don't know what to do here. But in Python, in contrast, say, to Fortran, when we're using mypy today, we're going to sort of add this static typing on. We're going to have a procedure beforehand that lets us check the types of our program, and we're going to have some way of specifying types. Now, this won't be intrinsic, because if mypy says no, we can still run it and still actually run this code and get something out. Maybe we never hit that error, or maybe we get some partial information and then eventually we stop. So it's still a different kind of paradigm to Fortran. Now, what about languages without types? Well, I mentioned assembly language. In a sense, assembly language does have a type, but there's just one type. It's just bits. Everything is just a sequence of bits. Perhaps there's a kind of length to them, but they're always bits. And everything just works, but then the operations might not do what you want them to do. So if you're writing code by hand in assembly language, like just the language of your processor, you have to sort of track everything in your head and sort of try and keep track of, oh, the register holds this thing and this is what it means, and I don't want to use this bit of the data and so on. And it makes it very difficult. And this is part of one of the reasons why programming languages that we have now, high-level programming languages, are so powerful. They offload the meaning into the language. We don't have to keep so much in our head. Right, so mypy. It's going to be this optional typing system for us that lets us add in additional types into our programs. We can do it a module at a time. We can choose which files to do. We don't have to do everything in a project. We can sort of add it gradually. And this lets us add these static checks on top. As I said, it's kind of the opposite of intrinsic typing. It's extrinsic typing. If mypy says no, well, we can still run it. And we're going to have type signatures that are a bit like the math notation I showed you. OK, so here's our first bit of mypy. It's Python code, but now we've got this type signature in here. And actually, Python, the language, back in Python 2, this would be not valid syntax. But in Python 3, they said, OK, we're going to actually support this syntax so that you can add type signatures in like this. And the Python interpreter will just ignore them. Like the PyPy interpreter will just ignore them. Any other kind of Python interpreter will ignore them, but mypy will actually have a look at that. So here's our first two bits of code. So here I've defined just a single variable, flag, and I've given it the type bool. And here I've defined a function plus, and I've said, OK, the first argument has type int, the next one should have type the next one should have type int, and this returns something of type int. So we've got this arrow notation of the function type. We've got our inputs, our arguments with their types here, and this is the return type of the function. So we can do return x plus y. OK, so I'm going to start writing more code. So let's have a brief pause, and you can install mypy yourself if you don't have it already. You can install it via pip. You could probably just write pip install mypy, or you can do it in this way, -m pip install mypy. Or maybe this is takes you to the documentation of how to install it. So I'll just give you a moment to do that. You might also want to, if you're using VS Code or something else that has it, another IDE, you can install the plugin, which will kind of give you the mypy information directly in your IDE. So you might want to install that as well. I'll be using that as well. I'll do a mix of both. Yes. Yeah, good question. So the question is, does mypy help with performance optimization? The answer is no. It doesn't change the way that Python's doing anything. This is really just a set of verification checks. So it doesn't then use that to optimize. Okay. I'll just give people a moment. If anyone's stuck, perhaps put your hand up and I can. Yes. Yes. Mm-hmm. So the question is, what's the difference between Black and mypy? And perhaps that will become more apparent as we kind of get into it. But as a kind of high-level answer, so what Black is doing is suggesting changes that will not affect the meaning of the code. It's the secondary notation, it's the layout, it's the variable names, it's the structure, and they don't actually change the program, those things. But in mypy, we'll be getting information that says, no, if you run this, there's going to be a problem, so you should change your code so that it does something different. So mypy is going to be telling us that we should be changing our code if there's going to be a typing problem. But hopefully, as we go on, that will be clear. Thank you. It's a good question. Yeah. Yes. Is there an occasion when to prefer dynamic typing over static typing? We'll come back to this. This is a good question. There are kind of limits to static typing. So sometimes there might be things that will run fine, but mypy says no. But we know that they're OK. So that's an issue to do with something called completeness. And we will come back to that and deal with that. So that's a very good question. Yeah. OK. So think we can do some things. So I'll write some code as well. So we had on the slide that this was x plus y. And I'm going to add in what was on the slide, these type signatures. So this is Python. This is valid Python. I can run this. I'm going to add in that information that this is. We're expecting this to be int, 2 ints as inputs and an int as output. Now, what you can do, you've probably heard of test-driven development. That's when you write tests first before you write your code, because you're thinking, what's the specification of this code? That's the kind of the key thing in test-driven development. It's forcing you to step back and think, what do I actually want this code to do? And you can do the same with types. We can do type-driven development, where we first write down the types of our functions, and then we implement them and check, did we implement code that matches that specification? So maybe I do this, and mypy is going to complain at this. So let me show you, sorry, what I should show you first is we can run the mypy tool directly on our code like this. And in this case, it's given us back an error. It says on line 8, I've got incompatible return value type. I got str, but I expected int. So mypy has analyzed the code. It was saying, I expected it to be int because that's what you wrote in the specification. You specified that you thought it was going to be an int, but I analyzed it and I got something that was a string. That's str. And so we're told we've got this error. And I have the plugin installed for Visual Studio Code, which is what I'm using. So we can also see that error up there as well. So I go, no, OK, that's not what I wanted to do. I just wanted to do plus. And now the squigglies go away. Let me run mypy, and we get green, and the green makes us feel happy. Success, no issues found in this one source file. So we have a bunch of primitive types in our type language provided for us by default with mypy. We've got int, we've got bool, we've got float, we've got string, str, and we've got this thing called none, which is often used in Python when we sort of essentially don't have any information in our result. So for example, I'm going to write a function called greet, which takes a string. But it's going to do some side effect. I'm going to sort of print out the value. So I'm going to say its return type is none. And what I'm going to do is then say print hi plus name. So the return type of print is this value none. Let's check mypy's fine with that. OK. So when we execute this, we'll get some side effect. We'll get something printed out, but it doesn't actually return as an important value. Oops. Sorry, that's something I forgot to comment out. Yes, Joseph. Yep. For the plus function, yeah. But it returns an integer. Yeah. Yeah. OK. So if I want a string to be returned here, well, then I need to change my specification, because my specification says it should be an integer. So if I change my mind, sure, I can do that, but I should change my specification if I want if I want mypy to be happy. So yeah, if I do greet and I give it a number 42, then mypy is going to say, look, there's an incompatible type here. I expected this to be string, but you're giving me an integer instead. but otherwise that's going to be fine. MyPy says that's fine. I can run it. I get hi everyone. I guess I should have reminded us what happens if we have something else. So there's one of those runtime type errors. Type error can only concatenate string, not integer, to string. So we can see what happens there. That's the runtime realization of the fact that this thing is not well typed. Let's have another example. Let's do one with floats. So I'm going to make the myabs function. I'm going to take a float as input and say, well, if x is less than 0, return minus x, else return x. And yeah, that's fine. Okay, people having success with trying these, those who are able to try it? Great. So there was that example. So these names that we've been using, int, str, bool, and so on, they exist in this language of types. We call them type constructors because they are constructing an object, I probably shouldn't use the word object, an entity in the type language. Now there are some constructors that behave like functions on types because they take one type and they give you another back. Here's an example that you'll already be familiar with, but perhaps you haven't thought about it in this way, the concept of a list. When we want to talk about the type of a list, we need to think about the types of the elements. We can't just say, oh, this thing is a list, because, well, a list of what? Is it a list of integers? Is it a list of floats? Is it a list of netcdf files? You know, what is it? So we say that for some type T, then we can describe the type of lists whose elements are of type T like this. So we use the square brackets. It's almost like list is it's a type function almost. Well, it essentially is a type function. And it's taking this type as an input, and this thing is itself a type. It constructs a type in our language out of another type, and it captures the list of all elements of that type T. So for example, let's say I want to write this function greetAll, which I guess I'll type out in a moment. It takes a list of strings, and it loops through them and prints them all out. And again, this has type none. So let me write that, because then I'll modify it in a moment. In fact, I'm going to call this greetAll list. So actually, I can use my greet function from before. Great. That's better. OK, and what did I write there? Nonsense. OK, good. So list of names. We go through them all. We print each one out. Our greet function, we knew that that took a string and gave back none. So it's putting all of the information about the types together there. And now we can use that. If my computer lets me write things. OK, I'll write some things in a moment. There we go. OK, so of course I can run this and I get the things. OK. Let's think of another data structure then, which has more type information we need to think about, so tuples. So when I have a tuple, I'm putting together bits of information which could have different types. It's heterogeneous. A list is treated homogeneously. In Python, everything inside should have the same type, according to mypy. With a tuple, it's heterogeneously typed, so we have many of these type arguments. And this is like the A cross B notation on sets. So if I want, I can do the following. I've got, okay, some data here. It's a triple. It's a tuple with 3 things in it. So I'm saying, okay, its components are int, bool, and string. And now I can put all of those things together in that package. And I've got my signature here that describes the type of each one of those things. So that's a nice and straightforward way of describing the type of a tuple. Okay? And we can do this with tuples which have 2 things, or 3 or 4, or so on and so forth. It generalizes to arbitrary sized tuples. Other data constructors that we're used to are the data types. There's the dictionary. We often use that in Python. Now, with a dictionary, we have two types of entity inside that we have to describe. There's the keys of the dictionary, and there's the values. So the dict type constructor takes 2 arguments, k and v, and it tells us what are the type of the keys and what are the type of the values. So if I have something like this, here the keys are strings and the values are floats. Okay. Now, you might be thinking, what about if I want to have a function that returns things of 2 possible different types? That is possible using this operator that's called the union operator. In Python 3.10 and below, you actually had to write the word union, but if you're using greater than 3.10, which some of you probably are, then you can use this pipe symbol instead. So we can do something like the following. In fact, I'm just going to type it out. I'm going to think about this function called mydiv. No, we're not going to do that yet. We're going to do mydiv, mydivide, which takes an x, which is a float, a y, which is a float, but it might fail because division by 0 we want to be an error. So if x equals 0, then I'm going to return none, and otherwise I'm going to do x divided by y, like this. So by using this pipe, this union, I'm saying there's 2 possible outputs here. It could be a float, or it could be the none thing. So let's just compose these 2 things together. It's a type function taking 2 different types and giving us another type. Yes? Oh, yeah, thank you very much. Yeah, good. See, exactly. So, perfect. The types let us guard against some errors, but not all errors, right? They don't deal with everything. Let's check mypy. Everything is good. All right. So there we go. I had it right on the slide. In fact, I flipped the logic in the slide, but that's fine. So Python is an object-oriented language. That means we can create classes. And every class name also then becomes a type constructor. So example, if I make a complex class, I want to have these objects that belong to that class that contain 2 parts, say a real part and an imaginary part, then when I build one of these things, when I use its object constructor, I can say, OK, this has type complex, like this. So every class that I define, its name goes into my type language. It's now something I can refer to from my mypy types. So I've got that in here somewhere. I'm doing things in a different order apparently, but let's bring that in. The demo gremlins. my computer's just frozen. I know, or at least, oh, there we go. Yeah, that's very high load averages. What's thrashing it? Sorry, pay no attention to this. I'm just trying to work out why my computer's being so slow. No, it's not that. It wasn't at the top of the list. Right, so there's the class. That all works fine. Right, and we're going to go back to generalizing in a moment. think I'm missing a slide. So what I will do is, oh no, I think I just changed them. So one thing you can also do with mypy is actually ask it for what it thinks the type of something is going to be. So you can use this function, reveal type, within an expression, and when we run mypy, it will tell us what that thing is. So if I do, let's think now, let's say I'm interested in the type of some of the things in the standard library. I want to sort of work out what their type is. I can write reveal type, and then, okay, I'm going to do length in this case. Let's see what happens. So mypy now gives us this note about what the type of that thing is. So it tells us it's a function, it's a def, and it takes something from typing.sized. We don't really know what that is, but it's okay. We can get some intuition. It's something about things which are sized, and it gives in a built-ins.int. So that's just an integer that we know already. So we can inspect the types in that way. We can ask mypy, what does it think? If I run Python on this now, then we're going to get this error that says, hey, I don't know what reveal type is. This is not a function I know about. So you can actually sort of guard against this by importing from the typing library. We can import, I'm just going to do the thing I need from in typing, import this Boolean called type checking, and then I can do this here, if type checking, and so when I run Python, this flag is going to be false, but when I run mypy, it's going to run it with the flag as, well, it's just analyzing the code. So this is a way of kind of, if you really want to keep that in there, probably not, but if you really wanted to, and you wanted still, maybe you're in the development phase, and you're kind of, I want to be testing code and checking mypy, but I want to keep these reveal type things in, you can deal with it by having this conditional here. So we'll never run reveal type if we're not type checking. So there's an example. Right, subtyping. This is where things get more interesting. So as we said, Python is object-oriented. Part of its implementation of the kind of object-oriented ideas is that it has a hierarchy between its classes. We can think of one class being the subtype or a supertype of another, and you can inherit from another class and become part of this hierarchy. So in going back to some notation, we say that A is a subtype of B, written like this. A colon less than B, and we can kind of think of this a bit like subsets, right? So if something is in A and A is a subtype of B, then it's also in B. So as an example, we've been using list, but list is actually a subtype of the iterable class. Things that are in the iterable class we can do for loops over. So we could actually take the function that we had before, and which was the function on list, this kind of greet all thing, and we can actually generalize it to work on not just things that are list, but things that are iterable. So I could have taken iterables that contain strings and then return none like this. And I'm actually going to, yeah, I can do for name in names again. Greet name. So there are other things than lists which are iterable. For example, all of these things here. So, okay, lists of strings, but I can also take dictionaries, I can also take tuples. All of those things are iterable. Let's check mypy is happy. It's not, because the iterable comes from its typing interface. Like that, okay, and let's run Python on it. Okay, so we can see that we could iterate all of those things. I had a list of strings, I had a list of dictionaries with string keywords. It said that's fine, I'm going to iterate over the keys and also over the tuple as well. Okay, we've already done that one, that's good. Oh, okay, these were in a slightly wrong order. There's that example of, here's an example of that union type happening again. This. Okay, good. So going back to a kind of a theory idea again, so if we had a function that went from type B to type C, and we also knew that A was a subtype of B, and we also knew that some expression x is of type A, then we're allowed to put all of these things together and give x to the function f and actually apply it. We can think of it as this function is expecting to do things with input that conforms to the type B. But if x is a subtype of that, A, then it can also do everything, you can do anything to that value that you can also do with a B thing as well. So we can provide that here. We can provide, say, like a list to this previous function and still get some result out C as well. So we read this line as like, if we have all of these things above it, then we have the thing that's below it. We can do this typing, and that's a valid typing. Okay, so we've gone and we've done that, that example, that's fine. Okay, little pause, just check there's any questions or comments. Yes?
There like a output, like negate something?
Yes, so question is there something kind of universal like any? That's what we're going to do right now. So perfectly predicted. Okay, so what if a function's type is too specific? So let's say we have this function called first, takes a list of strings, and it returns a string. What does it do? Well, it takes that input, which I've called x's. Yeah, not a great name, but it's fine because there's not really necessarily much we know about it. And we're going to do the indexing at position 0. So we'll return the first thing in a list. Is it really important here that it's strings? I mean, what if we wanted to do something similar, but we wanted to use lists of ints as well? Barring the typo, where this should have been lowercase, this is exactly the same implementation, right? The implementation is the same. Again, the code here it's more general than strings or than ints. So if we wrote this function and then later on we were like, oh yeah, we want to do it with ints as well, well, because of the strictness of mypy, we'd have to write list int thing like this as well, but now we've got 2 bits of code, and duplication is bad. We should try to write as little code as possible. If we've got duplicated code, well, we have to sort of maintain both things as well, and we don't have a single definition that we can explain and point to. So we might think about trying to have something more general here, and for this we could use this constructor that's called any. So we can import this constructor from the typing library, it's called any, and we could define the function like this and say, well, for a list with any elements, we return something with any output. So in mypy, we can always use any, and any will always work, and you can type anything with any, essentially. So this is kind of like a way of dealing with this. It's a way of taking these 2 things and unifying them into a single definition. But as a specification, it's not really that great. It's a very general specification. It's not very tight or specific to this example. There are many, many functions that have this type, list any to any. There's lots of other things we could do that have that type that do all kinds of things. Let's see. Okay, I'm just going to black that for a second. So we can do our what was it called first? So from typing, import any. So I wanted to do list of any and get an any out. Here's another example which has exactly the same type. Takes in an input, never does anything with it, and returns some very large integer. This also has the type list any to any. So this list any to any specification is not really that great, doesn't give us very much information. Any hides so much stuff, and really is not very flexible. So we'd like something that's more powerful here. We would like to be able to describe this function in a much better way that really reflects what it's doing. And for this, we can use something called parametric polymorphism, also known in some languages as generic types. So in essence, we want to generalize that definition to say that this works for a list of any type, but then the return result has to be the same type as the type of the elements. So what we can do is introduce a type variable in using the following syntax in mypy. We can introduce this thing here called type var t. We have to give it a name as a string, and it has to match this part over here, the variable name. But then we can use that t in the definition, and we can read this implicitly as having a universal quantification, as having a for all. This says for all types t, if I have a list of t's, then I get a t out. And now this exactly describes the kind of function that takes a list and pulls out one of the elements. We can no longer just return an integer here, because this function, we could use it on lists of strings to get a string, or lists of netcdf files to get a netcdf file. If we put an integer, well, that wouldn't match any possible t that we could put here. So we can think of this as whoever uses this function, they're going to provide a list, and mypy will automatically work out then what that t is going to be in that specific instance, in that specific function call. So if I give it a list of cats, that t is going to be cat. If I give it a list of strings, that t is going to be string. So let's do this. We have to import something else again. We have to, from typing, import type var. And then I'm going to say t is a type var, that. And now I can take that original definition. I'm just going to yoink it out, comment that. And I can turn this from any to t, much more descriptive. Whoops, mypy, everything's happy. And if you're using Python 3.10, I think you have to include this word type here for that to work. So if you're in that situation, you might need to do that. And here's some examples. Now I can use this function on inputs of different types. So I can use it with a list of integers, I can use it with a list of strings, and of course that's fine, and that would be fine in normal Python. And now mypy is happy with that as well, because I've used this concept of a type variable. We call it parametric polymorphism. Polymorphism is like many shapes, many forms. Parametric is that we have this parameter, this type parameter, that we're using in the function, telling us what the type of those elements are going to be. And OK, if I reveal type on example 1, of course that's going to say string. And if I reveal type on example 0, that's going to say int. And yep. And if I then try to return some long and complex number here, then mypy is going to be sad and say, no, I expected this to be t, but what I got was actually an integer. So it's the person who's calling this function, it's the code that's calling this function that's going to determine that t. So as far as the function is concerned within itself, it has to work for every t, which means it can't go and mess around with the elements inside of the list. It can't go and do some operation with the elements in the list. All it can do is take that list, do some stuff, take it apart, take one of those elements, and return that element, which we do there. Of course, this would work for other elements in the list, but that's the only way we can get a t back. It's really, really descriptive, this parametric polymorphism. It's really constraining the kind of functions that we can write here, which is good. That's what we want specifications to do. We want specifications to reduce the space of possible programs that we could write. Yes?
It's fine. Fine, like that's how far it's reduced out.
Yeah, this is a great question. So what's the scope of this T? So I can now write other functions that also use that T. So it's not sort of specific to that place that I wrote it, but it's really saying now I'm using it here. It doesn't link these two functions together. It's really just saying I have this name that I can use implicitly as a universally quantified type. And yeah, I could write last like that. And so I could use first and last with different types. That would be fine. In fact, you can see that I'm using them all with various different things here, and that's okay. That's not going to. They're not sort of what is it in Python? True, false, like this. Thanks. They're not kind of linked by that. Yeah. Great question. Yes. Yeah, so the question is, what if I want to sort of set it access to none? Straight away, mypy is going to complain with that because it says, no, this thing has to be a list T. But I could perhaps do this, and now that's okay. I could say, well, this was either a list T, this variable holds either list T's or nuns, so I can reassign it to none. Now this is bad because I can't index on a none, but yeah, hopefully that answers your question. I guess, what is it in, could probably do something like this. I'm not sure that, I'm not sure how to do, I'm not sure that this will work. Because it doesn't do what's called path-dependent typing. It doesn't propagate the knowledge that that's a type down to that thing. But we can talk about that offline. That's getting into the weeds of something else. So let me fix that, but this is a good question. OK. So what I think we will move to now is you trying some more stuff on your own. I'm going to skip this and we'll come back to it because it gets a bit complicated. Let's talk about function types. So one of the ways of programming in Python is to use functional programming principles. That's where we program with functions as our primary organizing principle. We can take functions as first-class parts of our language, so they're treated as data. They can be passed in as inputs, and they can be returned as outputs. Lots of stuff in Python is organized in this way. So we can describe the type of functions directly as pieces of data. So we can do that using the callable type constructor. So if we have a function that takes n inputs, which we're going to describe with the types a1 to an, and a return type b, then we describe that in our type language like this. We say it's a callable. Callable takes 2 arguments, but this thing here is a whole kind of group of arguments that describes the type of every input. So that's the type of the inputs, and that's the type of the output. So if we go back to our set notation, it's like saying a1 cross a2 cross a3 cross an arrow b. And that's just represented using this callable interface. So what example am I going to do? Let's see if I can remember it or check my iPad. Right. So I'm going to do from typing import callable. I'm going to make a slightly silly higher order function. I'm going to call it memo. It takes a function and an argument, and it returns that argument and the function applied to it. So where have I got a reveal type? Okay, so if I import tutorial and I do tutorial.memo, so what was its definition? I give it a function and an argument, and then it applies the function to the argument. So let's do lambda x plus 10, and I give it an input. There we go. So I'm giving it this lambda function, I'm giving it an anonymous function, which takes an input and adds 10 to it. So I get that pair with that original input and the output. Apologies for people who are on the side, probably can't see what that says, but hopefully you can imagine it. Or I can do this, and you don't have to imagine. So what's its type? So this here is a function, and I'm going to introduce some more type variables. I'm going to call them S and T. We already had T. Let me call them A and B, actually. So it takes an A and produces a B. This thing has to have type A, and so the result is of type B. No, that's not what the result is. Sorry, it's a tuple of a and a B, of course. So quit out of this. Check mypy's fine. Yeah. So we've described the function input here, and got an example of tuple there as well. Okay. Everyone happy with this? Yes.
It's best to put type declarations in a block below your import statements and then carry on with all your functions in terms of just, structuring your overall code. So if you had multiple functions module which have their own unique type declarations, you put them in a block at the top of the module.
I don't know if there's a way to do that in mypy. So the question is, can we separate out the type specifications from the functions itself and put them in a single block? Pass. I don't know if there's a way to do that. I actually personally think even if you could do that, the answer would be no. Because I think it's very useful to be able to look at a function and see that information there, right? This is communicating something to you. So it's metadata, it's documentation. That's another great thing about types. They communicate to the reader as well. They tell them, it gives you some information about what this thing's going to do. So I think having that localized is a good idea. It doesn't supersede all kinds of documentation. I'm not writing doc strings in here because that's not what this thing is about. But if you were using this in a real project, we would definitely advocate for you also putting in the doc strings and having that documentation. And these types are also giving you extra information as well. So we have function types. Okay, I've been talking for a while. There's a worksheet here with an exercise for you to try. So please have a look at that and give it a go now. We'll have maybe 15 minutes to do it. I'm not expecting you to necessarily finish it, so if you don't finish it, don't worry. There's a few things I want to say after this, so I'll leave myself 10 minutes to do that. After the exercise, and I'll circulate around and take this off. Yes, the question is, what about other libraries? We'll actually do NumPy after the break, after the little worksheety break, but it's a good example. So as I mentioned, every class goes into the type language, so there will be something you can say about those other libraries based on if they introduce any other classes or if they're using existing types. Many libraries come with their own typing definitions, and that includes NumPy, which we'll see in a moment. But you could, if the classes on their own sort of don't suffice, you can build up your own additional typing on top of that by creating little interface classes, for example. And there are ways, to do it in a bit more of a lightweight fashion as well. But many of the big libraries do have a dot typing submodule or something, and we'll see the NumPy one very briefly at the end. That's a great question. So I'll post the link to the repository on the Slack once I'm done with this, and that has also the link to the solutions and all the examples here, so you can kind of keep on with that worksheet and then check against the solutions when you're done. So there was something that I kind of skipped over because I wanted to get to the worksheet, and that's something going back to this parametric polymorphic types thing. So there's something really special going on with these specifications, something that really gives us a lot of information, and that's the fact that we can actually start to understand more about what that function's going to do based on its parametric polymorphic type. And that's something called what we get from it is something called a free theorem. So let's imagine that you were just told that a function had this type. For all t, list of t to t. Well, that type tells us quite a lot about what it actually does. The universal nature of t, the fact that this has to work for all t's, tells us that we can't actually inspect or compute with those elements t. We can't sort of take one of those elements and do something with it, like add to it, or do a conditional based on it, or use some other operation that's sort of data specific. It really, all we can do with it is give it away to another function or return it, or just not use it. So this implies a property which in mathematical literature is known as a naturality property. So let's assume we had some other function, which I'm just going to call f for succinctness, that goes from of type s to t. For some particular type s, some particular type little t. So that means that we could use the sum function on that little t. So we can take a list of little t and get a t back, and then we can, done it the other way round. We can take f and apply that to that input. Sorry, to the output of some fun. So I'm doing this as a diagram. You can think of this as a chain of functions. We're going to take some input of list t, give it to some fun, get that t output, and then give it to the function f and get something of type s out. So that's sort of this expression down here. We're going to do some fun applied to a list argument and then apply f to the result. But this is going to be, the type tells us that this is equivalent to doing the following: taking a list t, mapping over that list with f to get a list of s. So that's transforming every element of the list using the map function on lists that applies that function f to every element, and then getting the list back and then applying some fun on it to get the thing s as the result. So this is the naturality property that follows from the types. So this is an optimization essentially that it's describing, because going this way round on this side, we only apply f once. We apply it to the output. But on the other side, we have to go through the list, we have to traverse that whole list and apply f lots and lots of times. So we have to do the computation of that f the same number of times as the length as the input, and then apply some fun. So this over here is going to be more efficient than running this thing over here. And that follows from this typing. There's a whole bunch of maths about why this is the case. But there is a caveat here that that's really only true in languages that don't have side effects, that can't do some sort of arbitrary side effects with like mutating some state like a global variable, or doing some printing input and output and things like that. If we assumed that these were kind of pure functions, they didn't have side effects, then this property would hold. So this sum fun is going to do something like pick one of these elements of the list. Let's say it's the first one, we don't know, it's just going to pick one of them and give it back to us. So this way around, it's going to pick one and then we apply f to it. This way around, we're going to transform all of the elements and then pick that particular one. And these are the same. They do the same thing, but one of them is faster than the other. And so we're going to talk about things that are of that ilk in the session tomorrow that's called What Can Abstract Mathematics Tell Us About Programming Climate Models? I'm going to talk a little bit more about that kind of thing there. If that's just a little bit too much, then don't worry about it. Also, you don't feel like you have to come to this thing. There's other stuff happening that is also very interesting at the same time. OK, so any quick questions about that before I talk about NumPy? Oh, yeah. No, can't do that. The function can't sum every element in the list, because that means I have to do plus on those elements, and this works for all t. And you can't do plus on a t that's every t because it could be a string or a cats or something like that. Good, great, you know, thank you. You were thinking about it like, what if, but it's this for all. It's this polymorphism. If this was just a list of integers to integer, then you're right. I couldn't say this naturality property. This naturality only comes from the parametric polymorphism. So types, they can really, especially polymorphic types, they can really refine down that space of possibility, so we can even reason about the programs without even looking at their definitions. This is a very cool area of programming language theory. All right, happy to talk over beer about that as well. Right, so we had a really good question about other libraries. One that you'll probably want to use is NumPy. As I said before, all class names get added into the type language. So if I'm using NumPy, then I can talk about ND arrays in my type signatures. So that's the normal class name, the objects in NumPy for the arrays. So here I've imported NumPy as NP, and I can say, okay, my array is of type np.ndArray, and just do some constructor like that. But of course, I might want to talk about the fact that I have an ND array of floats versus an ND array of integers and so on. We haven't got down to that kind of type parameters thing yet without adding some more things in. So NumPy provides a bunch of typing information as well via its typing submodule. So I can import numpy.typing. I'm going to give it a name here, mpt. And this gives us various things. It gives us a type constructor called array-like, which is a sort of super type of a bunch of things. It describes objects that can be converted to arrays. There's also dtype-like that describes things which are dtypes in the sort of NumPy parlance. And then it gives us this parametric type, this type constructor, ndArray t. So we can talk about NumPy arrays of t values. So, and there's a warning that you probably need to, if you're doing this, you need to add a mypy.ini file, which tells mypy to use the NumPy type mypy plugin as well. I put that into the repository as well in case you need it. So here's a little example. I can do something like the following. I can have this function that's called asArray. It takes something A, which is array-like, and it calls the boring function that turns it into an ND array. That's not using the special type. It's using array-like. But I can also do something like the following. This is scale array. It takes a float and an ND array of float 64s and gives us back an ND array of float 64s, and it does that operation. So we've used the parametric types here to specify that this should only work with float arrays. So just like we were doing with the lists, where we could specify the elements with this capital ND array, we can specify the type of the elements inside our NumPy array. So there's other things that it provides. You can sort of dig into the documentation to see what is provided by that library. But essentially, many of the key libraries that are popular will have a typing, a bunch of extra typing definitions to make it interact well with mypy, using principles we've talked about today. Okay, escape hatch. So we had a very good question here earlier on about what if, I can't quite remember the question, it was sort of, what if there are things that mypy doesn't like but actually are fine. So this is about a completeness. A type, we can describe a type checker like mypy. It's a type checker. It's a type checking algorithm. We say it's complete if they're all, if we can imagine the set of all possible valid programs, P. If for each one of these programs P, then TP says yes, this is fine, this is a valid program. So basically, it doesn't reject anything which we haven't decided is valid. mypy is not complete. So there are programs that we might want to run that are never going to produce runtime errors that mypy, we won't ever be able to come up with a type for in mypy. So what do you do then? Most type checkers are incomplete. You kind of get to this problem. In mypy, there is an escape hatch where you can write this afterwards. We can write hash for a comment, type, ignore, and mypy just won't be run on that expression. So you shouldn't really need to use this, or at least not in production code. But if you're kind of halfway through doing something and you're still trying to work out what its type is, maybe it's a good sort of like, well, I can use it now, but I'll remove it later. Just remember to remove it later. So, OK, I can't do 0 divided by a string, but I can put this on, and mypy will ignore it. So I think I had that at the bottom of this code somewhere. There we go. Of course, if I run that, it will break, but mypy is going to ignore it. If I took that out, then mypy is going to be complaining. So there's an escape hatch.
Are there any non-topological examples where the type checker wouldn't find the problem? Sorry.
So I think once we start getting into doing dynamic, having code that depends on the type dynamically, gets into this kind of issue, where we're saying, well, we'll look at the type of this object and then decide to do different things depending on it. Those kind of examples, I think, are one of them. But we can have a play later. OK, so we're getting to the end. So what have we done today? What have we learnt? Well, hopefully we've learnt how to understand some key ideas in specification and verification. I started very high up because I wanted to kind of bring these concepts into view. Some of the key terminology behind types, we've talked about sort of static versus dynamic, these kind of different paradigms of type languages. We've talked about sort of type constructors, Cartesian products, function types as well, and a few other things around that. We had our sets model. We talked a bit about subtyping. That was a little bit, didn't get time to go deeper into that. You can look more into it, but we touched on that, and we've talked about this idea of parametric polymorphism. I should say, in the object-oriented world, often the word polymorphism means this kind of overloading that you get because of the subtyping hierarchy. This is the word that's often used in object-oriented context. Other bits of the literature call this overloading, or they call it ad hoc polymorphism. What we did today is more specifically known as parametric polymorphism, where you've got the function and it behaves uniformly with respect to some part of the type information. And well, why did I show this picture here? Because we learnt about getting rid of bugs in our code using mypy. So we've seen how mypy gives us this extrinsic static typing. We can still run our code even if mypy says no, but it gives us this set of extra checks that helps us avoid bugs. And it also gives us documentation as well. So I hope you'll go and sort of finish the worksheet. Do start using it in your projects, and I think it's relatively smooth to get going on. And once you start building it in, you kind of get used to it. And yeah, it helps produce quality code that's going to run well. It provides documentation as well as that layer of verification. So thank you very much. Have fun going and doing typing. Cheers.